Hi, in this video we are going to talk about pH, pK, and buffers. You all know that acid is a compound that gives a proton, and base is the one who accepts it. The first term we are going to discuss here is the dissociation constant, which is Ka. This is the ratio between the multiplication of the product's concentration and the acid concentration. Strong acids dissociate almost completely, while weak acids dissociate to a less extent. This means that strong acid has high Ka and a weak acid has low Ka. And of course the same goes with bases. Well, some of you might find it interesting when they know that water itself can act as a base and acid. This is because water molecules can dissociate into a proton and a hydroxide ion. But one thing to notice here, protons do not exist as individuals. In fact, they are hydrated by water molecules to produce a protonated water molecule called hydronium ion. Let's have a look at this small amount of water. The probability to find a proton at any given time is 1.8 multiplied by 10 to the power of minus 9. This means that for every 1.8 billion water molecules, we'll find one that has dissociated into one proton and one hydroxide ion. And if, for instance, we have double the quantity, in this case 3.6 billion water molecules, we'll of course have 2 protons and 2 hydroxide ions. Okay, let's try to find the dissociation constant for the ionization of water. It will look the same as the equation we used for the acid. The concentration in these equations is in molar, which is the number of moles per liter. Since we know that the density for water is 1, so 1 liter, which is equal to 1000 cubic centimeter, will weigh 1000 grams. And to calculate how many moles of water we have in a liter, we will divide the weight, which is 1000 grams, by the molecular weight of water, which is 18. 2 for the 2 hydrogens and 16 for the oxygen atom. This is equal to 55.56 moles. Since water is a monoprotic acid, which means that one water molecule can have only one proton and of course one hydroxide ion, this means that we will have equal concentration of protons and hydroxide ions. In order to calculate their concentration, we'll have to multiply the probability of their existence by the concentration of water, which is 1 multiplied by 10 to the power of minus 7. And here is our equation, but there is still one more step to go. 55.56 molar is a huge number, so we can safely consider it as a constant. And since K is also another constant, there is no meaning to have two constants in one single equation. So we'll multiply both sides by 55.56 and combine the two constants into a new one called Kw. Since Kw is equal to the multiplication of proton and hydroxide ions, it is called the ion product of water. The value of Kw, which is 1 multiplied by 10 to the power of minus 14, is measured at 25 Celsius. And since this value is constant, we should know that as the proton's concentration increases, the hydroxide ion's concentration decreases, and vice versa. Now let me introduce a new term, which is P. P means the negative log of anything which the P is assigned to. Okay, I know that some people might feel irritated when they see the logarithmic functions, and not all people like math. I'll try to do my best to simplify the rules of this function. When we say the log y is equal to x, we mean that when the base is raised to the power of x, it will yield the value y. So what is the base? The base is the small number written underneath the word log, which by default is equal to 10. This means that when 10 is raised to the power of x, we'll have y. A simple example is log 100. When 10 is raised to the power of x, yields 100. X is therefore equals to. Another simple one is log 1000. Here the base 10 has to be raised to the power of 3. If we use another different base, in this example 2, and we try to calculate log 8, it will be 3. Now here are some rules you should know while dealing with logarithmic functions. The first rule is, if we have a term involving multiplication inside the logarithmic function, the result is equal to the addition of log each term on its own. Now I'll prove for you that this is correct. Let's say we have log 10, which we all know it's equal 1. we can assume that this is not 10, it's 2 multiplied by 5. So we'll calculate the log of 2 and 5 on their own and add them. Log 2 is equal to 0.3 and log 5 is equal to 0.7. So you can see that both sides are equal. Now the second rule. If the term inside the logarithmic function is raised to any power, you can safely remove this power out of the function and multiply it by the result of the function. For instance, if we have log x to the power of 2, this function is equal to 2 multiplied by log x. And let me prove it for you. You now know log 100 is 2. 100 is also 10 to the power of 2. So log 10 to the power of 2 is 2 multiplied by log 10, which is 1. Finally, the last rule, which is the opposite of the first one. If the term inside the log function involves division, the whole function will be equal to the subtraction of log each component of the term. Confused, huh? Let's have an example. Log 100 divided by 10, which is of course, 10, is equal to log 100 minus log 10. Log 100 is 2 and log 10 is 1. And of course 2 minus 1 is 1. In pure water, we knew previously proton concentration is equal to 1 multiplied by 10 to the power of minus 7. Applying the minus log to the proton concentration, we'll have the pH, which is 7 in water, because it's neutral. And of course, the pOH will be of the same value. Applying the P to the ion product of water, Kw, we will have the value 14. This is why the pH scale is 0 to 14. 0 when we have an acid only and 14 when we have base only. So why do we use P and these log functions? Why don't we just use the concentration of the proton? This is because we have very wide range of possibilities of proton concentration. To clarify more, let us just imagine not having this P or log function. pH values of 7 or 13 or 1 will mean that the concentration of protons are 0.6 O's 1 or 0.12 O's 1 or simply 0.1. It's obvious that dealing with the pH scale is much better. Ka's and pKa's can be used to show the strength of acids or bases. Acids with high Ka's have low pKa's and they are considered strong acids. Acids with low Ka's will have high pKa's and of course they are weak acids. By the way, monoprotic acids which produce only one proton per one molecule have 1 Ka and 1 pKa. Diprotic acids which can give 2 protons, such as sulfuric acid, has 2 Ka's and 2 pKa's. Each proton has its own Ka and pKa. The same goes with triprotic acids, like phosphoric acid. It has 3 Ka's and 3 pKa's.